Everyone talks about radar. Everyone knows the Allies had it. Everyone knows it changed the war. But almost no one talks about what the Germans built on the other side of the English Channel, and almost no one talks about how good it actually was. Not just good, frighteningly good. Good enough that on certain nights, in certain conditions, German radar operators knew Allied bombers were forming up over English airfields before those planes had even crossed the coastline. 4 hours before the first aircraft reached German territory, the warning bells were already ringing. The plots were already being drawn. The night fighters were already being scrambled. If that sounds impossible, stay with me. Because the story of how Germany built one of the most sophisticated early warning and air defense systems in the history of modern warfare is one of the most underappreciated stories of the entire Second World War. And it involves physics, psychology, deception, mathematics, brilliant engineers, stubborn generals, and a cat-and-mouse game fought not with bombs, but with invisible waves bouncing through the dark. If you want to understand why this matters, you have to go back to before the war even started. Back to a time when radar wasn't a household word, when most military planners still thought of air defense in terms of searchlights and sound detectors, when the idea of electronically tracking a fast-moving aircraft in the dark still seemed closer to science fiction than operational reality. In Britain, the story is well known. Robert Watson Watt and his team developed Chainhome, the network of towering transmitter masts stretched along the southern and eastern coasts of England. It was crude in many ways, limited in resolution, limited in accuracy, unable to determine altitude with precision, but it worked well enough to give fighter command the edge it needed during the Battle of Britain in 1940. Radar gets the credit for saving Britain, and in many respects it deserves it. But Germany wasn't sitting still. Germany had been working on radar detection technology since the early 1930s, and in some key technical areas, German radar was actually more advanced than anything the British had built. The Germans didn't have one radar system. They had a family of them, each designed for a specific task, each feeding information into an integrated air defense network that was designed from the ground up to do one thing above all else: stop bombers from reaching their targets in the dark. The name of that system was Kammhuber Line. Named after General Josef Kammhuber, the Luftwaffe officer who built it almost entirely through sheer force of will, against constant resistance from above. And before we get deep into the technology, you need to understand the man, because you cannot understand the system without him. Josef Kammhuber was not a glamorous figure. He wasn't the kind of general who appeared on propaganda posters. He was methodical, technical, stubborn, and deeply serious about the problem he had been handed. In 1940, after the fall of France and the beginning of the RAF's early bombing campaign against Germany, Göring assigned Kammhuber the task of building a night fighter defense. The assumption at the time was that this would be a simple job. Night bombers were slow, bombers flew in predictable paths. Night fighters with good pilots could handle them without any help from electronics. Kammhuber disagreed. He had seen what happened when you sent a night fighter into the dark without guidance. You got nothing. The aircraft flew around in the blackness, the crew saw nothing, and the bomber got through. Night interception without radar guidance was almost impossible. He understood this early, and he made it the core of his entire philosophy. Every element of the system he built, every radar installation, every communication link, every control room, was designed to solve a single fundamental problem. How do you put a fighter exactly where a bomber is when both are moving through complete darkness at hundreds of kilometers per hour? The answer was zones. Kammhuber divided the likely approach corridors into a series of overlapping defensive boxes. Each box was roughly 30 kilometers wide and 20 kilometers deep. Inside each box, a radar system tracked everything that flew through it. A single night fighter was assigned to patrol that box, and when a bomber entered the box, a ground controller watching the radar plot would talk the fighter onto the target step by step, vector by vector, until the fighter was close enough to find the bomber visually, or with its own onboard radar. One box, one fighter, one controller. Repeat this across hundreds of kilometers of European sky, and you have the Kammhuber line. But to make this work, you needed radar. Not one type, but several, each doing a different job. The first piece of the puzzle was long-range detection, something that could reach out far enough across the Channel, far enough over the North Sea, to give the German air defense system the time it needed to react. The system that did this job was called Freya, and Freya was remarkable. Freya was a rotating radar, which was already a step beyond what the British Chainhome system could do. Chainhome was fixed. It stared in one direction and couldn't move. Freya rotated, sweeping its beam in a continuous circle, painting the sky ahead of it every few seconds with a fresh radar picture. Its range was extraordinary for the time. Under good conditions, Freya could detect large formations of aircraft at distances exceeding 200 kilometers. That's not a typo. 200 kilometers. When you do the math on that, when you calculate how long it takes a bomber formation cruising at around 300 kilometers per hour to cover 200 kilometers, you get something very close to 40 minutes. But the operators watching Freya weren't just detecting planes. They were observing behavior. And this is where the story gets genuinely fascinating, because the Germans developed a sophisticated understanding of how Allied bomber operations actually worked. A major bombing raid didn't begin when the planes crossed the Channel. It began hours earlier, in English airfields scattered across East Anglia and Lincolnshire and Yorkshire. The bombers had to be fueled, armed, and checked. The crews had to be briefed. The aircraft had to start their engines, taxi to the runway, and take off one by one. A raid involving several hundred aircraft took a long time to get airborne. Then those aircraft had to assemble. Assembling hundreds of bombers in the dark over England into coherent formations was a complex process that required navigation aids and designated assembly points and a considerable amount of time. This assembly phase, the circling, the forming up, the climbing to altitude, this produced a very distinct radar signature over England. Freya operators watching from across the Channel could see this. They could watch the aircraft count over English airfields, climb from a handful of returns to dozens, then to scores, then to numbers that left no doubt. Something big was coming, and they were watching this process from the very beginning, from the first aircraft that took off, which was, on many nights, 3 to 4 hours before those aircraft would reach the German frontier. Think about what that meant operationally. The German radar network didn't just have 40 minutes of warning. In many cases, it had several hours of strategic warning. Hours during which night fighters could be positioned, fuel could be allocated, crews could be rested, and then woken and briefed. Hours during which the entire defensive apparatus could orient itself toward the expected threat axis, because the assembly pattern over England often gave away not just the size of the raid, but the rough direction it would come from. This wasn't accidental. German signals intelligence and radar interpretation had developed to a level of sophistication that we rarely give it credit for. The operators who watched the Freya screens were trained to read the patterns. A big circular assembly over East Anglia meant one thing. A long line of returns climbing over Lincolnshire meant something else. Radar returns over the Norfolk coast climbing to a different altitude than returns over Kent suggested different target priorities. The Germans were reading the Allied air order like experienced card players reading faces across a table. But Freya had a limitation. It was excellent at range, it could see far. But it was poor at precision. It could tell you that a large formation was forming over England and moving generally in a certain direction, but it couldn't give you the fine detail needed to put a night fighter onto a specific bomber. For that, you needed something else. You needed a precision radar. And Germany had one. It was called Würzburg. The Würzburg radar was a masterpiece of German engineering. Where Freya was large, long-ranged, and somewhat coarse, Würzburg was compact, powerful, and extraordinarily precise. It used a parabolic dish antenna that focused its radar beam into a narrow cone, which gave it the ability to track individual aircraft with an accuracy that was genuinely startling by the standards of the early 1940s. A Würzburg set, properly operated, could track a target in 3 dimensions, giving bearing, range, and altitude simultaneously, updating continuously as the target moved. In the Kammhuber system, each defensive box used 2 Würzburg sets. One tracked the bomber. One tracked the defending night fighter. The controller watching both plots on his display table could see exactly where each aircraft was at any given moment. He would talk the fighter toward the bomber using radio instructions, guiding the aircraft to converge on the target. When the 2 plots came together on his screen, it meant the fighter was within visual or short-range radar range of the bomber. At that point, the interception was a matter for the pilot and his radar operator. This sounds elegant on paper. In practice, it was extremely difficult. The bomber crews were not passive. They maneuvered. They dove, turned, climbed, and dropped bundles of metallic foil to confuse the radar. The controllers had to anticipate, predict, adjust. The night fighter crews had to deal with darkness, weather, disorientation, and an enemy that was actively trying to kill them. But when everything worked, when the radar chains passed their information up the line correctly, when the controller was experienced and cool, when the fighter crew was skilled, when the atmospheric conditions were clean, the Kamm-Huber system could be devastatingly effective. In 1941 and 1942, losses in the RAF's bomber offensive climbed to levels that alarmed the command structure. Crews were completing their tours with difficulty. Some squadrons were losing aircraft at rates that threatened their continued existence. The Kamm-Huber line was working. Not perfectly, not consistently, but well enough to make the night offensive expensive, in a way that forced the RAF to think hard about how it was operating. The Germans continued to refine and expand. Freya stations multiplied along the coastlines of occupied Europe, creating an early warning network that ran from the northern tip of Denmark down through the Netherlands, Belgium, France, and into the Mediterranean region. The coverage was not uniform. There were gaps, there were terrain problems, there were equipment failures and maintenance issues. But the overall picture was of a system that was improving with every passing month, incorporating lessons learned from each raid, plugging gaps that bombers had exploited, replacing equipment that had been destroyed by commando raids or precision attacks. There was one Freya installation that attracted particular Allied attention. It sat on a clifftop at Bruneval, on the French coast near the mouth of the Seine. Intelligence reports, partially developed from analysis of aerial photographs and partially from information provided by French resistance networks, suggested that this installation contained radar equipment of great technical interest. In February 1942, British paratroopers landed near Bruneval in the dead of night, fought their way to the radar installation, stripped critical components from the Würzburg set that was installed there, and were extracted by sea before German forces could respond in strength. The Bruneval raid was significant for several reasons. First, it gave British scientists their first direct look at German radar technology. They were able to examine the captured components, understand the wavelengths involved, understand the design philosophy, and begin developing countermeasures. Second, it demonstrated to the Germans that their coastal radar installations were vulnerable, which led to increases in security at installations across occupied Europe. Third, and perhaps most importantly, for the long-term intelligence picture, it confirmed what some Allied analysts had suspected. German radar was technically sophisticated, well-built, and in some respects ahead of what the Allies had expected. The scientists who examined the Bruneval components were particularly interested in the wavelength at which the Würzburg operated. This was critical information, because the effectiveness of electronic jamming depends entirely on knowing the frequency of the equipment you're trying to jam. If you don't know the frequency, you can't jam it. Now they knew, and the race to develop effective countermeasures began in earnest. But before we get to the countermeasures, we need to talk about what the Germans were doing in the meantime, because they weren't standing still either. One of the most important developments in German radar capability during the middle years of the war was the development and deployment of airborne radar for the night fighters themselves. If the ground-based Würzburg could bring a fighter to within a kilometer or two of a bomber, then an airborne set could close the final gap. It could allow the fighter crew to find and approach the bomber without needing to see it. The system the Germans developed was called Liechtenstein, and it was remarkable. Liechtenstein was a radar set small enough to fit inside a twin-engine fighter, with an antenna array fitted to the nose of the aircraft that looked like a forest of metal rods sticking forward into the airstream. It created considerable aerodynamic drag, which cost the aircraft some speed and maneuverability. The crews initially hated it for this reason. Some pilots refused to use it. They preferred to rely on their eyes and the visual cues available in moonlight. But as the war went on and the bombing increased, attitudes changed. The fighter crews who mastered Liechtenstein found that they could hunt in conditions where eyes were useless. On heavily overcast nights, on nights with no moon, in conditions where a bomber was completely invisible at any range greater than a few dozen meters, Liechtenstein could find it. The combination of Freya, for long-range warning, Würzburg for ground-controlled interception, and Liechtenstein for the final approach, created a layered system that was far more capable than anything a single technology could have delivered. Each layer compensated for the limitations of the others. Freya saw far but coarsely. Würzburg saw precisely but at shorter range. Liechtenstein saw at close quarters in the dark. Together, they formed a chain that ran from the English airfields where the bombers were assembling all the way to the moment of visual contact in the dark sky over the Reich. And then came Window. Window was the British codename for bundles of aluminum foil strips cut to specific lengths and dropped from aircraft in large quantities. When a bundle of window was dropped from a bomber, it created a cloud of radar reflections that appeared on German radar screens as a cluster of aircraft returns. Drop enough window, and the radar screen filled with false echoes. The controllers watching their displays couldn't separate real aircraft from the chaotic blizzard of returns. The Würzburg sets, which had been so precisely tracking individual aircraft, suddenly couldn't track anything with confidence. Liechtenstein sets in Night Fighters showed a screen full of false targets. The whole elaborate system, the carefully coordinated ground control, the patient vectoring of fighters, the precise tracking of both pursuer and pursued, it collapsed into confusion. Window was not a new idea. The British had developed the concept of radar-obscuring metallic strips some time before they actually used it. The reason they held back was that they were afraid of giving the Germans the idea. The Allies also had radar installations protecting their cities and convoys. If the Germans adopted window after seeing it used against their own radar, it could make the defense of Britain and Allied shipping much harder. So window sat in a file, approved but not deployed, until the scale of losses in the bomber offensive made the calculation clear. The cost of not using it was higher than the risk of the Germans copying it. Window was used for the first time on the night of July 24th to 25th, 1943, during Operation Gomorrah, the massive attack on Hamburg. The effect was stunning. German radar operators watching their screens saw them fill with countless false returns. The carefully maintained plots of bomber formations dissolved. Night fighters sent to intercept found nothing their radar could lock onto. The attack on Hamburg was one of the most devastating of the entire war, and the German air defense system was effectively blinded for critical hours. The Germans called window Dupel, after the place where their own researchers had conducted experiments with a similar concept. And the German scientists had indeed developed the same idea independently. They had even been worried about the Allies using it, which was one of the reasons they had not deployed it themselves. Now that it had been used against them, the restrictions were lifted, but the damage was done. Hamburg burned. But the Germans adapted. They always adapted. The response to window came in several forms, and understanding those responses tells you a great deal about how technically capable the German air defense establishment actually was. The first response was a new tactic called Wild Sow, which translates as wild boar. Developed by Major Hajo Hermann, Wild Sow abandoned the ground-controlled interception model entirely for single-engine day fighters operating over defended cities. The idea was that the fires started by bombing, the searchlight beams and the glow of the burning city itself would provide enough illumination for a skilled pilot to see and attack bombers visually. The ground radar network couldn't track individual aircraft through window, but it could still tell roughly where the bomber stream was. Single-engine fighters, stripped of their dependence on radar tracking, could orbit over the target area and find bombers in the light of the flames. Wild Sow had mixed results. It required exceptional pilots willing to operate in the middle of their own flak in the dark, which was both dangerous and psychologically demanding. Some pilots were killed by their own anti-aircraft guns. Others were lost to weather or disorientation, but on good nights, the tactic worked. Bombers silhouetted against the fires below were visible to a circling fighter in a way they never were in the open dark sky. It was primitive compared to the radar-guided interception model, but it was a response, and it showed that the Germans were capable of tactical innovation under pressure. The second response was Zahme Sow, or tame boar. This was a more sophisticated solution that addressed the fundamental problem window had created. If ground radar couldn't track individual bombers through the chaotic window returns, then perhaps the night fighters could navigate the bomber stream by using other methods. In Zahme Sow, night fighters were guided not to a specific aircraft, but to the general area of the bomber stream, using whatever radar information remained available. Once in the stream, the fighters used their own Liechtenstein sets, combined with a new piece of equipment called SN2, to find individual targets. SN2 was a new airborne radar that operated on a different wavelength from the original Liechtenstein. Because window had been cut to specific lengths tuned to jam the original Liechtenstein frequency, it was much less effective against SN2. The Germans had essentially changed the frequency of their airborne radar, and the window that filled the sky on every raid suddenly became much less useful against the new sets. It was a classic electronic warfare exchange. One side found a way to blind the other, and the blinded side found a way to see again. SN2 had its own limitations. It had a relatively wide beam, which meant it wasn't as precise as the original Liechtenstein at close range. It also had a dead zone close to the aircraft where it couldn't detect targets properly, but its immunity to window made it enormously valuable. By late 1943 and into 1944, night fighter crews equipped with SN-2 were finding their way back to something approaching their previous effectiveness. There was another piece of the technology puzzle that deserves attention, because it represents one of the most creative applications of electronic intelligence in the entire war. The Germans developed a system called Naxos and another called Flensburg. These were passive receivers, meaning they didn't transmit anything themselves. They simply listened. What they listened for was the radar transmissions of Allied aircraft. By the middle of the war, many Allied bombers were equipped with the H-2S radar, a ground-mapping radar that allowed navigators to see the terrain below them and navigate to targets with much greater accuracy than dead reckoning allowed. H-2S was a genuine advance in bomber navigation capability, and it was responsible for improvements in the Allies' ability to find and hit targets in bad weather. But H-2S had a fatal characteristic. It radiated. It transmitted radar pulses downward, and those pulses didn't all stay beneath the aircraft. Some of them propagated outward in other directions. Naxos was a receiver built into German night fighters that could detect the radar transmissions from Allied H-2S sets. When a bomber flying through the dark had its H-2S turned on, it was broadcasting its position to any aircraft equipped with Naxos within a certain range. The night fighter crew didn't need to rely on ground control vectors or their own radar transmissions. They could simply home in on the radar emissions of the bomber itself. The bomber's own navigation aid was becoming a beacon that guided its killers to it. Flensburg did something similar, but targeted a different Allied device. The Monica radar was a rearward-looking warning radar fitted to many RAF bombers to detect night fighters approaching from behind. It was designed as a protective measure, a way for the crew to know when a fighter was closing on their tail. But Monica also radiated, and Flensburg could detect those radiations. A bomber equipped with Monica and H-2S was broadcasting on two separate frequencies, both of which German night fighters could home onto passively, without giving away their own position. When this was discovered by British intelligence, the implications were horrifying. Equipment designed to protect bombers was instead helping to kill them. Monica was withdrawn from service. Restrictions were placed on H-2S use. But for a period of time, German night fighters had a capability that the Allied crews knew nothing about. They were being hunted by aircraft that could find them in total darkness without active radar, without any searchlights, without any of the visible signatures that crews were trained to watch for. The weapon that Zamesau night fighters used to exploit this capability most effectively was called Schräge Musik, meaning jazz music or slant music, a reference to the angled nature of the attack. Schräge Musik was an installation of upward-firing cannon mounted in the fuselage of the night fighter, angled forward and upward at approximately 60 to 70 degrees. The tactic was for the fighter to slide into a position directly beneath the bomber, in its blind spot. The bomber's ventral gunner position, if it had one, often couldn't depress far enough to engage a target directly below. The belly of the aircraft was vulnerable. Once the fighter was in position beneath the bomber, the pilot would align his sight and fire upward into the wing roots or the bomb bay. The aim was not to kill the crew immediately, but to ignite the fuel tanks or the bomb load. A bomber hit in the wing root by an upward-angled cannon burst would start burning almost immediately. The fire would be visible to other bombers in the stream, but often, the crew of the stricken aircraft wouldn't even know they had been attacked until it was too late. No tracer coming at them, no flash from below. Just a sudden burst of fire in the wing or a catastrophic explosion. RAF crews were aware that something was killing them in this way. They saw bombers exploding around them with no visible attacker. They heard the explosions. They saw the flames tumbling down through the stream. But for a surprisingly long time, the cause was unclear. Some crews thought it was German anti-aircraft shells fitted with proximity fuses. Some thought it was mines suspended in the sky. The idea that fighters were sliding underneath them and firing upward was suspected, but not confirmed for months. When the truth was finally established through a combination of captured German documents, prisoner interrogations, and the analysis of damage patterns on aircraft that returned after being hit but not destroyed, the response was to fit downward-looking radar and ventral gun positions to more aircraft, and to train crews to watch below as carefully as they watched behind and to the sides. But the weapon had been lethal, and it had been lethal in part because it was invisible. It exploited a blind spot, both literally and figuratively, in the Allied defensive awareness. All of this technology, the the Freya stations watching English airfields, the Würzburg sets tracking bomber streams, the Liechtenstein and SN2 sets in the night fighters, the Naxos and Flensburg receivers homing on Allied radar emissions, the Schräge Musik cannon firing from below. It was all part of a single integrated system. A system that could engage bombers at every phase of their flight, from takeoff to target to return. And at the apex of that system, feeding it all together, was the Kammhuber Lines reporting and control network. The reporting network was organized in a way that looks almost modern to contemporary eyes. Information from Freya stations was passed upward to regional reporting centers. Those centers combined the radar tracks into a coherent picture of the incoming raid. That picture was then displayed on a large plotting table where controllers could see the entire tactical situation. Fighters were plotted on the same table. Controllers at lower levels received sectors of the picture and directed fighters in their area. Night fighter wings had their own operations rooms where controllers worked the radio, talking fighters toward their targets. The most sophisticated element of this was the Seeberg table, which was a transparent plotting surface illuminated from below. Red dots represented bomber tracks. Blue dots represented fighters. The controller could watch the two sets of dots and guide the fighter to intercept, ordering changes in heading and altitude by radio until the dots converged. When they did, the fighter crew would either see the bomber visually or pick it up on their onboard radar. The Seeberg table was a genuine human-machine interface, designed specifically for the problem of night interception, and it worked well enough that it remained the core of the German night fighter control system until the end of the war. The communications infrastructure supporting all of this was equally impressive. Landlines ran between radar stations and reporting centers. Radio networks connected ground controllers to night fighters. Telephone circuits linked the various levels of command. There were dedicated communications channels for each defensive box in the Kammhuber system. There were backup channels for when primary circuits were disrupted. The whole thing was designed to continue functioning even if parts of it were damaged, because the Germans knew the Allies would attack radar installations when they could. And the Allies did attack radar installations. Special operations teams sabotaged facilities. RAF aircraft bombed Freya stations. American fighters strafed radar equipment in low-level attacks. Commandos, as at Bruneval, raided specific installations to capture equipment. But the network was resilient. It had redundancy. When one station was destroyed, adjacent stations extended their coverage. When a Würzburg was knocked out, a replacement was brought forward. The Germans were not complacent about protecting their radar network, and they invested heavily in making it difficult to destroy permanently. There was one vulnerability, however, that proved extremely difficult to address. The relationship between the early warning radar network and the assembly of bomber forces in England had a physical limit that the Germans couldn't engineer around. Freya could see far, but it couldn't see forever. At ranges beyond 200 kilometers, returns became unreliable. At ranges beyond 250 kilometers, even large formations disappeared into the noise. The English Midlands, where some bomber groups assembled, were at the edge of Freya's reliable detection range. And as bomber assembly procedures were refined and modified in response to German interception patterns, the Allies found ways to make the pre-crossing phase of the raid less legible to German operators. But the fundamental physics of the problem still favored the defender in one key respect. A bomber formation moving at cruising speed has a fixed relationship between detection range and warning time. You can't make a large formation invisible when the radar technology capable of detecting it is operating at maximum range. And the Germans continued to push the boundaries of that range. By 1943, some Freya variants had been upgraded to ranges approaching 300 kilometers. Some experimental installations were claimed to achieve even greater ranges under favorable atmospheric conditions. There was also a phenomenon called anomalous propagation, which occasionally allowed radar signals to travel much farther than their design parameters suggested they should. Under certain atmospheric conditions, particularly on calm, cool nights with a strong temperature inversion near the surface, radar waves could be bent back down toward the Earth by the atmosphere itself, extending their effective range dramatically. German operators learned to recognize when these conditions were present and to give extra weight to returns that appeared at unusual ranges on such nights. There were cases, documented in post-war analysis, where German radar returns from over England were obtained at ranges that should theoretically have been impossible, and where the timing of those returns relative to actual raid departures confirmed that what had been seen was genuinely the assembly phase of an Allied bombing operation. The intelligence integration feeding the German air defense system was not purely radar-based. Signal intelligence played a role. The Germans were monitoring RAF radio communications, and while the Allies were careful about operational security, the sheer volume of radio traffic associated with a major bombing operation generated signatures that were discernible to experienced analysts. Pre-raid increases in specific types of radio traffic, changes in the patterns of aircraft radio check procedures, alterations in the scheduling of ground control transmissions, all of these created an electronic fingerprint that preceded a major raid and could contribute to the warning picture alongside the radar data. There were also human intelligence sources, agents in Britain, spies within or near bomber airfields, individuals with access to information about operations. These were a feature of the intelligence war on both sides. The effectiveness of German human intelligence in Britain was significantly constrained by the double-cross system, through which British intelligence had turned most German agents operating in Britain and was feeding false information back to the Abwehr through them. But even the managed intelligence flowing through compromised channels could sometimes contain indicators that were useful to the German defense if processed correctly. Meteorological data was another input. Both sides were acutely aware that weather was a critical operational constraint on bomber operations. German meteorologists tracked weather patterns over Britain and the North Sea, and their assessments were integrated into defense planning, a developing weather window over England that would allow the assembly of large bomber formations and the conduct of an extended mission was itself a risk indicator. German air defense stood to a higher state of alertness during periods when the weather forecast indicated favorable conditions for Allied bombing operations. It was a probabilistic system, not a certain one, but it contributed to a situational awareness that went beyond what radar alone could provide. When you put all of these sources together, the long-range Freya radar watching the assembly, the signal intelligence monitoring the radio traffic, the meteorological assessment of operating conditions, the human intelligence filtered through the double-cross system, you begin to understand how a German air defense commander in 1943 or 1944 could have a reasonably accurate estimate of what was coming several hours before the bombers crossed the channel. Not a certain estimate, not a perfect picture, but a picture rich enough to make decisions, to position fighters, to allocate fuel, to prepare the control rooms. The limitations of the system were real and significant. The defenders faced the problem of scale. By 1943, RAF Bomber Command was dispatching hundreds of aircraft on a single night. The Kammhuber system, designed around the concept of one fighter per defensive box, had been built to handle a rate of bomber penetrations that corresponded to earlier, smaller raids. As the raids grew in size, the single-box single-fighter model became a bottleneck. Only one fighter could be guided in each box at a time. If a large bomber stream was threading through a box at high density, many bombers would transit the box before the single assigned fighter could re-engage after an interception. The math was brutal. You could potentially score kills at a constant rate, but if the bombers were coming through faster than you could turn your fighter around, the effective kill rate per bomber declined. The Allies understood this before Kammhuber did, and they deliberately exploited it. Bomber Command, under Air Marshal Arthur Harris, began concentrating bomber streams, compressing the time during which the stream transited any given area. Instead of spreading raids out over several hours with aircraft trickling across the coast at intervals, the new tactics sent hundreds of bombers through a narrow corridor in the shortest possible time. This concentration didn't make individual aircraft safer, it actually increased the risk of collision, but it overwhelmed the Kammhuber system's capacity to handle multiple interceptions simultaneously, diluting the kill rate per aircraft even as it concentrated the weight of the attack. The stream tactics, combined with the window countermeasure, the shift to Zam-Sao guided interception, and the continued expansion of the bomber force, created a situation by late 1943 where the battle was genuinely balanced on a knife edge. Both sides were taking serious losses. Bomber Command's loss rates in certain operations were approaching levels that threatened the sustainability of the campaign. German night fighter losses were climbing as Allied escort fighters pushed deeper into German airspace, and as the sheer number of bombers in the sky increased the probability of fighter-bomber encounters. The Americans had joined the strategic bombing campaign with their own approach, daylight precision bombing, by heavily armed formations of B-17 Flying Fortresses and B-24 Liberators. The American approach relied on mutual fire protection between aircraft in tight formations rather than on the cover of darkness. This meant a different set of radar-related challenges for the German defense and a different set of tactics in response. German day fighters attacking American bomber formations had to deal with dense defensive fire and, increasingly, with long-range escort fighters. But the radar network's contribution to the defense against daylight raids was also significant, because the same Freya stations that watched RAF formations assembling at night were watching American formations assembling by day. The American 8th Air Force's operations from England followed patterns that were visible to German radar operators, and the intelligence derived from those observations fed directly into the allocation of German fighter resources between the eastern and western fronts. When the radar picture showed a major American formation forming up over East Anglia, fighter units held back for anti-bomber duty would be stood to, fuel would be pumped, pilots would be briefed. The early warning time that Freya provided against daylight formations was, if anything, even more useful than against night raids, because daylight interceptions required more preparation and coordination to execute effectively. One of the most significant engagements in the entire radar war was the catastrophic Allied raids on Schweinfurt in 1943. Schweinfurt was a city in central Germany containing factories that produced a large percentage of Germany's ball bearings, components essential to almost every mechanical system in modern warfare. Destroy Schweinfurt's factories, the planners argued, and you would cripple German industrial production. The raids were deep penetration missions, flown without adequate fighter escort, and the German radar and fighter network had time, warning, and resources to mount a serious defense. The first Schweinfurt raid in August 1943 was costly. The second, in October 1943, was catastrophic. The German network tracked the American formation from the moment it was visible to coastal Freya stations. Fighters were scrambled in waves. Some engaged the formation over France. Others waited to engage over Germany itself, as the formation's escorts reached their range limit and had to turn back, leaving the bombers unprotected. Fresh German fighter units that had been vectored into position ahead of the stream swept in. 60 American bombers were lost, many more were damaged. The loss rate was unsustainable. The lesson of Schweinfurt was not that strategic bombing was impossible. It was that strategic bombing without adequate escort at all altitudes and throughout the entire mission was suicidally expensive when the defender had the radar warning time to position his forces correctly. The German air defense network had done exactly what it was designed to do. It had seen the formation forming, tracked it across France, coordinated multiple fighter units to engage at chosen points, and inflicted losses that forced a temporary halt to deep penetration missions. The Americans drew the correct conclusion. What was needed was a long-range escort fighter capable of accompanying the bombers all the way to the target and back, engaging the German fighters that the radar network was vectoring onto the bomber stream. The aircraft that solved this problem was the P-51 Mustang, fitted with drop tanks to extend its range to over 1,000 kilometers. When Mustangs began appearing over Germany in early 1944, the entire calculation changed. The German radar network could still detect, track, and vector. It still gave hours of warning. But now what the German fighter pilots found at the end of those vectors was not an unescorted stream of bombers. It was a stream of bombers surrounded by highly maneuverable, long-range escort fighters flown by trained and aggressive American pilots. The German air defense commanders faced an impossible choice: attack the bombers and take devastating losses from the escorts. Stay back and let the bombers through. The escort fighters changed the strategic equation in a way that radar tracking and vectoring could not compensate for. But the radar war continued to evolve even as the operational situation shifted against Germany. The Germans continued to develop and deploy new radar systems. One of the most significant was the Mammut, a large fixed phased array radar that offered ranges even greater than the Freya and better resistance to jamming due to its different beam characteristics. Another was the Wassermann, a tall rotating radar that provided more accurate height information than earlier systems. These were not improvised stopgaps. They were serious engineering achievements produced by Germany's scientific establishment even as the overall war situation deteriorated. The Allied response continued in parallel. Electronic jamming became increasingly sophisticated. Aircraft were equipped with airborne SIGAR, a jamming system designed to disrupt German night fighter communications. Mandrill was a noise jamming system designed to interfere with Freya's radar returns. Corona was a particularly clever operation in which German-speaking RAF personnel broadcast misleading instructions to German night fighter crews on the same radio frequencies used by German controllers, creating confusion about which voice to trust and which orders to follow. At one point, German night fighter controllers were issuing one set of instructions, while British Corona operators on the same frequency were issuing contradictory ones, and the fighter crews genuinely couldn't tell which was real. The electronic battle had reached a level of complexity and sophistication by 1944 that would not have been imaginable 5 years earlier. Both sides were operating integrated systems combining radar, communications, intelligence, and active countermeasures. Both sides were adapting rapidly to the other's innovations. Both sides understood that the technical dimension of the air war was as important as the number of aircraft or the skill of the pilots. Germany's air defense radar network had one other capability that is worth discussing in detail because it directly influenced how both sides thought about operational planning. The network's ability to track bomber streams in real time meant that German commanders had an accurate and continuously updated picture of exactly where the main bomber effort was at any given moment. This sounds obvious, but its implications were profound. Before radar, a defending force had to guess where attackers would go and position accordingly, or wait until the attack arrived and respond after the fact. Either approach had serious limitations. Guessing wrong meant your forces were out of position. Waiting until arrival meant the attacker could concentrate before you could respond. Radar removed this ambiguity. A German air defense commander watching a real-time radar plot of a major Allied bombing raid could see exactly where the stream was, where it was heading, and at what rate it was progressing. He could make dynamic decisions about fighter allocation based on current information rather than forecasts or guesses. This capability also allowed the Germans to detect and respond to the Allied practice of using diversionary attacks to split the defense. Bomber Command often sent a smaller force on a different route, hoping to draw German fighters away from the mainstream and leave the primary target less defended. German controllers watching the radar picture could assess the relative size and heading of each group of returns and make a judgment about which was the main effort and which was the diversion. They were not always right. Sometimes the diversions worked, but the radar picture gave them far better information on which to base that judgment than they would otherwise have had. The Allies tried to deceive the German radar network in other ways as well. Aircraft called mandrel screen jammers would fly specific